We're now going to examine example 20.3. This circuit was also built as a lab to verify the numbers and to see how the circuit operates. This is an AC amplifier, where we can stick an AC signal here and get a much larger AC signal out here. So the first thing we want to do in analyzing the circuit is look at the DC conditions. So we'll do some basic DC analysis. And of course, the place we always start is at the base. So we want to, first of all, find voltage at the base. Now, the thing we have to consider is the input impedance into the base at this point. If Zin at the base is greater than 10 times R2, then voltage base is simply the voltage divider rule. So let's take a look at that first of all. Zin into the base of the transistor is equal to beta times Re. And in this particular example, we were told that the beta of this transistor was equal to 200. So here we have 200 times Re, 2.2K, and that equals 440 K ohms. Now 440 K, that in the base, is in fact greater than 10 times R2, which is 20K, because this only comes up to 200K. Now, because of this, we can now find what the voltage at the base is fairly easily. The voltage at the base is equal to VCC, 20, times the voltage divider rule, R2, 20K, over R1 plus R2, 150K plus 20K. And that number turns out to being about 2.35 volts. So that's the voltage right here at the base. The next thing we're going to do is we're going to find voltage at the emitter. And voltage at the emitter is simply equal to voltage at the base minus voltage base emitter. And so that simply means 2.35 volts minus 0.7 volts is equal to 1.65 volts. So there is voltage at the emitter. The next thing that we would want to do is find IE. And we remember that IE is approximately equal to IC. Remember, IE is approximately equal to IC. So IE is simply equal to VE divided by RE is equal to 1.65 volts divided by the emitter resistor, which is 2.2K. And that comes out to about 751 microamps. The next thing that we want to find out is the voltage collector to emitter. Find voltage collector to emitter. Now, because we're going to say that the emitter current and the collector current are basically the same, and we have that over here, the voltage collector to emitter is simply going to be VCC minus the drop across here and minus the drop across here, and that'll leave only the drop across collector to emitter. So VCE is going to be equal to 20 minus 751 microamps times the collector resistor, which is 12K, plus the emitter resistor, which is 2.2K, and that comes out to 9.33 volts. So there we have all the DC bias conditions for this transistor. And looking at the circuit from an AC perspective, the simplest thing to find, first of all, is the gain. And we could also find the AC voltages at this point, and at this point, and at this point in the circuit as well, if we were inclined. But before we know how big of a signal we could put in here to make sensible signals come out, we really should find the gain. Now remember, one of the characteristics of AC characteristics of this device, this transistor, is that intrinsically inside of it, it has a resistor called Re prime. This is an AC bulk resistance. And this value, Re prime, was equal to 25 millivolts divided by the DC current in the emitter. So we've already calculated what IE is, so we can calculate what Re prime is. Re prime is simply going to be 25 millivolts divided by 751 microamps is equal to 33.3 ohms. So there it is. Now, as we look at the emitter circuit over here, we notice that this DC resistor here, this Re, is completely bypassed by this capacitor. So because of this bypass capacitor, notice that Re is completely bypassed. Therefore, the AC resistance of this Re is equal to 0. So this is a crucial thing to note, because the entire AC impedance in this circuit over here, which would be Re, is equal to Re prime plus whatever is unbypassed here. And so in our case, we have this value, and this value is equal to 0. So the entire AC resistance in the emitter is equal to Re, in this case 33.3 ohms. The next thing we want to find out from this thing is, what is the resistance in the collector? What does the collector see as an AC source? Well, it sees a resistance this way to an AC ground, because that's a DC supply, and it sees a resistance this way through this capacitor, because this coupling capacitor essentially brings this resistor RL into parallel with RC. So we notice that RC is equal to the DC resistance in the collector in parallel with RL. And so when we calculate that, we find that in our particular circuit, RC is equal to 12K times 50K, product of the two, divided by the sum, which is 12K plus 50K, and that equals 9.68K. So that's what this collector sees as it looks towards the collector resistance and the load resistance. It sees 9.68K. Now, because the current in the collector is basically the same as the current in the emitter, the gain of the circuit is simply the ratio of whatever AC impedance it sees in the collector divided by whatever AC impedance it sees in the emitter. So the voltage gain of this circuit is equal to, in our case, the AC resistance, or the resistance in the collector, which is this, RC, divided by RE. So it's 9.68K divided by, and in the emitter we only have RE prime, that's the only one, which is 33.3 ohms. That means that the gain of this circuit is 291. If this circuit was capable of running, let's say, a 300 volt supply, what that means is one could put 1 volt in here and 291 volts AC would come out here. Well, of course, that's not realistic. So this tells us off the bat that with a 20 volt supply over here, we're going to have a gain of close to 300, that our signal here is going to have to be fairly small to still keep this in the operating region. This also helps us to understand why we did the DC analysis, because remember, we found that voltage collector to emitter across here, remember that, voltage collector to emitter, was equal to 9.33 volts. So that means that the biggest signal we could ever get out of the circuit would be about 9 volts peak to peak, if we could even get that. And so the input could not possibly be larger than the 9 volts divided by 291. If we did anything larger than that, the output would saturate.